Hello everyone, my name is Abdulazaz Al-Hamoudi. I'm a PhD candidate in the Computer Engineering Department at the University of California, Santa Cruz. Today, I'm going to be presenting Name Data Transport, which is designed to provide efficient content delivery by name over the existing IP internet. This is joint work with my co-author Professor J.G. Garcia at the Computer Communication Research Group at UC Santa Cruz. So the original use of the internet was to share expensive limited resources such as printers by addressing endpoint using IP addresses. However, the current internet usage today has been shifted toward accessing content such as video with platforms like Hulu, Netflix, or Facebook rather than to share resources. This can be seen from the right figure, which shows the high anticipated increase in the video traffic in the future. Also, mobility was not a concern back then. However, a big portion of today's traffic and in the future will be carried over mobile devices. And that's not just with cell phones, but with the breakthrough of Internet of Things, like in smart cities and Industry 4.0. In addition, the current internet leaves security to the end host. So all this results in many drawbacks when dealing with large data distribution, privacy, and mobility. The limitation of the Internet model to provide reliable and efficient access to content and services led to the development of dedicated solutions aimed at content delivery. These systems can be categorized as content delivery networks like Akami or peer-to-peer applications like BitTorrent. While such content delivery systems address many of the performance limitations of the basic Internet protocol stack, they require either third parties to provide added functionality or applications to replicate content delivery functionality independently of others. As a result, CDN and P2P approaches are insufficient to address the ever-increasing content-oriented usage of the Internet by all its users and applications. Several information-centric networking architectures have been developed to address the limitations of the IP Internet and the efficiencies of using CDNs and P2P applications. These architectures aim to allow all Internet applications and users to obtain content and services by name without requiring a specific system to serve different applications or forcing applications to determine where instances of content and services of interest are located in the Internet. One of the most popular ICN architecture is name data networking. NDN merges name resolution with routing to content and services. Name-based routing and forwarding in NDN have been considered to be necessary to attain an information-centric Internet. It's clear that NDN and other ICN architectures have produced valuable insight in what it means to provide information centricity at Internet scale. However, by requiring a far more complex network layer, using name-based routing to attain an information-centric Internet is only an architectural choice, not a requirement, that has profound implications. It means that efficient content delivery must come at the cost of redesigning the IP routing infrastructure. In addition, servers and clients must also be modified to adopt the APIs needed to use a name-based network layer, and widely successful applications like HTTP must be redone. IDNS and ICN are arguably the first proposed approaches aiming to provide the ICN benefits in the current Internet by leveraging the DNS system. Instead of resolving a URL hostname to an IP address, IDNS resolves content names directly to metadata that contains the address of servers hosting the content, taking into account local caches in the network. However, IDNS does not specify a specific protocol to retrieve content using its method, and instead leave it as part of their future work. ICN also uses the DNS to resolve a content name to a nearby cache or a hosting server, and uses HTTP as the baseline for the transfer protocol. The limitation of this approach are that it is limited to HTTP, requires the connection used in TCP, and which must take place at the application level, causing different types of caching proxy to be used for different applications. The contribution of our paper is to introduce an alternative end-to-end approach to an information-centric internet that we call named data transport. NDT aims to provide NDN benefits without the need to change the internet routing infrastructure or establishing a new overlays on top of it. The main goals of NDT is to allow all internet applications to request content and services by name rather than location. The second goal is to eliminate the performance issues associated with TCP connections, and the third goal is to making efficient use of a network caching for arbitrary content. The final goal of NDT is to prevent intermediate caches or routers from being able to decode cache content. NDT achieved the previous goals through the integration of three end-to-end architectural components. The first one is a novel transport protocol designed to deliver content reliably to consumers from content servers or transparent caches without the need for end-to-end connections as in TCP. The new protocol is referred to as Named Data Transport Protocol. The second architectural component is a manifest yielding DNS or MyDNS. It is used to provide near-replica routing of contents by mapping content names to one or multiple locations where the content is offered. The third architectural component is named data proxies, which are used to provide transparent caching of content at the transport layer while enforcing the privacy of consumers. Content names in NDT are based on DNS domain names, allowing them to be persistent and unique through the hierarchical nature of DNS. With the NDTP help, each content name on the internet is mapped to an individual manifest generated by its producer. A new resource record type, referred to as manifest record, is used to map the manifest of a content object to a list of IP addresses hosting a replica of the content. Each one of these addresses is added to the list as an individual DNS type A record. MyDNS updates this list as needed. This includes sorting the list by the nearest replica based on the consumer's geographical location, issuing the DNS query for the content name. Adding the manifest record to the DNS does not require massive change to the DNS architecture and only require an extension to the authoritative DNS and the local DNS server. This example shows how a consumer is able to resolve a content name to its manifest record and then start retrieving the content without the need for a connection. It starts with an NDTP producer publishing a manifest for a content to its My Authoritative DNS server. When a consumer needs to retrieve a content, it will resolve the content name to its manifest record using the local MyDNS. After the local MyDNS obtains the IP address of the authoritative MyDNS server, it will send a manifest query to it with the content name. Once it receives the manifest record, it will send it to the consumer, where it will start issuing interest immediately to retrieve the content without the need to set up a connection to the server. Applications running over NDT can be cached at the transport layer without the caching logic leaking to the application layer. It works by intercepting NDTP consumers' interests, distance for specific ports, or for a specific set of destination IP addresses. For example, we have a client here that sent an interest to the server but got intercepted by a router and redirected to the nearby MP cache. The MP cache surface the interest locally if a cache data packet with the same name exists in its content store. Otherwise, add the interest to its PIT table just as an NDN and get the data packet from the server using its IP address. The same interest could be intercepted again by other MP caches on the way to the server. If the MP cache receives another interest with the same name, it will add it to its PIT table to avoid sending duplicate packets to the server. Once it receives the data packet, it will cache it in its content store and use it to satisfy any pending interest. One way to prevent caches from accessing cached content is to use a session-based approach like TLS. However, this will preclude caching by establishing a closed end-to-end connection. Another solution would be to use group keys. For example, an NDTP producer will generate a new key for every new content, and only authorized consumers will have access to this key as part of the manifest. One problem is that members inside the group may know about other members in the same list simply by observing the chunks names being requested. Another approach would be to encode the data in a way only known to authorized consumers and producers. This is done by combining a content object with all chunks in the content store. However, data encoding alone is not sufficient to provide complete privacy in NDTP, but it could be enforced by using group keys to partially encrypt some of the coded chunks. As a result, consumers retrieving the same content will be requesting different set of chunks. And by using the group key, we are guaranteeing partial caching for all the chunks that are encrypted using the group key. We compared the performance of NDT, TCP, and NDN using our NDT implementation in NS3 and off-the-shelf implementation of TCP and DNS. In this experiment, we compared the total average time taken to retrieve multiple copies of a large data file using NDT, TCP, and NDN. The experiment consists of a source node connecting to a cluster of 6 consumers. All consumers start pulling the content from the source at the same time. Intermediate routers at the edge are configured to forward NDT traffic to MP caches, while routers in NDN can provide caching for any traffic that passes through them. As can be observed from the right figure, all three protocols perform very much the same when only a single consumer is involved. Now, as the number of consumers increases, the completion time in NDT and NDN remain constant. In contrast, the completion time in TCP increases linearly because all the data must be retrieved from the source. This highlights NDT's ability to take advantage of in-network caching as NDN does, but without requiring any changes to the IP routing infrastructure. The second experiment illustrates the inherent benefits of using a receiver-driven, connection-free transport protocol based on manifest. The retransmission and congestion control algorithm in NDTP are receiver-driven but are based on TCP congestion control algorithm. We compared both protocols assuming a scenario consisting of a simple network with a single source and a single sink. The consumer in NDTP issues interest for the content served at the other end after requesting the manifest for this content from the producer. The client in TCP consumes traffic generated by the server after establishing a connection with it using the TCP three-way handshake. The left figure shows the evolution of the congestion window for both protocols, where the growth of the window matches the expected behavior of the additive increase multiplicative decrease algorithm. The retransmission policy in NDTP allows receivers to detect and recover from a packet loss faster than in TCP. This is due to the fact that NDTP does not use connections and apply a fast retransmission strategy enabled by manifest. A consumer in NDTP has a complete picture of which chunks were received correctly and which were lost, and does not rely on partial acts like TCP does. The final experiment highlights how NDT's architectural components work together to provide efficient name-based content delivery over the existing IP Internet. We compared the total average time taken to retrieve a large data file in 3 cases, using only transparent caching enabled by NDT proxies. The second one is using redirection to nearest mirroring site based on MyDNS without transparent caching at NDT proxies. The third one is using NDT proxy together with the redirection to nearest mirroring sites based on MyDNS. The left figure shows an abstract view of the topology used in this scenario. In the right figure, we see the average latency incurred in retrieving the content object by a cluster of consumers arriving at random time. The number of consumers in each cluster was increased in each scenario. As seen from the right figure, when only NDT proxies are used, interest from consumers have to reach the producer site, and the benefits of using NDT proxies come from the aggregating interest and caching content. However, because of the short inter-arrival time of interest, only aggregation is useful in this experiment. In our scenario, with 10 consumers, only 10 interests for the same data object traverse the path to the producer. Using MyDNS without NDT proxies results in a shorter retrieval time for consumers, but duplicate packets are sent along the links. When both MyDNS and NDT proxy are used, interests from consumers are routed to the nearest mirroring site and aggregated at the NDT proxies. As expected, NDT performs best when NDT proxy and nearest replica routing through the MyDNS are used. This is because interests from consumers are routed to nearest mirroring site and aggregated at the NDT proxies as well.
In this presentation, we introduce named data transfer, the first ICN approach that attains efficient content dissemination without end-to-end connections or modification to the IP routing infrastructure. The design of NDT provides the same benefits of NDN through the integration of a new connectionless reliable transport protocol with name resolution and NDT proxies that support privacy-preserving online caching and native multicasting. To highlight the inherent benefits of the name-based connectionless approach used in NDTP, we implemented congestion and retransmission control algorithm similar to those used in TCP. Far more efficient algorithms can be adapted to be used in NDTP, and this is an area of future work. Similarly, securing the content and manifest records should be viewed as a starting point, and clearly more work is needed in this area. Making native multicast more efficient in NDT is another area of future work.